The physical restoration of Boeing B-17F serial 42-29-782 required reversing an invasive operational history. Robert Richardson acquired the aircraft in 1985. After his death in 1990, the Museum of Flight took ownership and began a major restoration the following year. What entered the project was not a pristine military bomber, but a heavily altered industrial machine whose decades of commercial use had fundamentally changed the structural geometry of the fuselage. The primary constraint was physical space. Commercial operators had cut openings through several bulkheads, altered floors, added access points, and removed military fittings to create space for civilian tanks and equipment. The investigative task was to determine exactly how much of the original 1943 factory standard remained intact beneath the commercial alterations. The airframe began its service timeline at Boeing Plant 2 in Seattle. It was officially accepted by the United States Army Air Forces on the 13th of February, 1943. Upon acceptance by the military, the aircraft was assigned stateside as a training platform. No combat service has been confirmed. Records indicate that the aircraft left the United States during a poorly documented overseas movement in 1944, possibly to Great Britain, before returning to stateside duties. Its lack of confirmed combat use spared it battle damage, but training service still subjected the airframe to continuous operational wear. The original factory configuration included standard defensive armament, heavy armor plating, and complex routing for military equipment. When the war ended, the specialized military utility of the airframe vanished instantly. The military no longer needed heavy bombers for training, and the aircraft was quickly declared surplus. The transition from military asset to civilian relic began through the War Assets Administration. In 1946, the aircraft was transferred to Stuttgart, Arkansas, for use as a memorial. Contemporary accounts associate the transaction with a payment of $350, although clear legal title later became disputed. The airframe was placed in a municipal park, where it remained on public display. This static period preserved the aircraft from the immediate post-war scrapping efforts that destroyed thousands of similar airframes. However, this static period ended in 1953, when the aircraft entered civilian ownership and was prepared for agricultural spraying. The firefighting conversion came later, around 1960. The operational demands of a commercial sprayer mandate raw payload capacity over everything else. This required a complete civilian eradication of the military interior. Agricultural aviation operations rely on the rapid dispersal of massive fluid volumes. To accommodate a 3,000-gallon chemical payload, the commercial operators executed a systematic gutting of the internal fuselage space. Every heavy component that did not directly contribute to basic flight control or fluid storage was permanently stripped from the airframe. Fluid tanks were installed in the nose, bomb bay, waist section, and beneath the wings. This civilian eradication process fundamentally altered the structural integrity of the aircraft. The original load-bearing bulkheads inside the fuselage were engineered by Boeing to transfer aerodynamic stress evenly across the airframe. To fit the chemical tanks used for mosquito control and later fire retardant drops, civilian crews cut openings through selected bulkheads and altered portions of the internal structure. The changes were extensive, but they were localized rather than a wholesale removal of the primary fuselage frames. All original military turrets were removed, and their mounting rings were plated over to seal the fuselage. Military armor and other heavy internal equipment were removed during demilitarization and civilian conversion, although the surviving records do not establish a single documented reason for every item discarded. By the time the museum took possession of the airframe, it had spent roughly 3 decades in civilian spraying and air tanker service. The exterior skin still retained the recognizable silhouette of a heavy bomber. The primary load paths had been interrupted, and the internal geometry was entirely dictated by the requirements of the civilian tanks. Identifying the missing bulkheads, mapping the severed load paths, and preparing to source replacement military hardware was only the first procedural hurdle. The engineering team had to assess the material condition of the remaining aluminum before any structural reconstruction could safely begin. How deep did the agricultural chemical damage penetrate into the original aluminum airframe? The primary challenge facing the museum engineers was not exterior weathering or typical aging. The new local constraint was the interaction between the civilian payload history and the specific manufacturing standard of the original interior. For nearly 40 years, the airframe had carried highly reactive fluids without any internal protective barrier. The outward appearance of structural integrity masked a pervasive internal breakdown that threatened the primary load paths of the entire fuselage. During wartime production, manufacturing speed, weight reduction, and the expected service life of a combat aircraft shaped factory finishing decisions. Large areas of Boeing-built B-17 fuselage interiors were left in bare metal, while zinc chromate primer was applied selectively in corrosion-prone zones and at certain material interfaces. This selective protection reflected wartime standards rather than a single aircraft-wide finish, or an assumption that the bomber would remain permanently dry. No designer planned for the same largely bare metal structure to spend decades carrying agricultural chemicals and firefighting residues. This bare metal baseline was standard for the era, but it became a critical vulnerability once the airframe transitioned out of military service and into the commercial sector. The largely bare metal interior was directly exposed to harsh industrial payloads. Agricultural operators reportedly used a kerosene and DT mixture for mosquito control work, and later carried fire-retardant compounds during aerial firefighting. Residues from these operations, combined with moisture and long service in a largely bare metal interior, created a serious corrosion risk for aviation-grade aluminum. The operational environment subjected the interior structure to constant chemical splashing, aerosolized mist, and vapor condensation over thousands of flight hours. Without continuous protective coating, residues and moisture could collect in seams, joints, and hidden crevices. Over time, corrosion consumed metal, attacked fastener areas, and weakened structural attachments from the inside out. The extent of that damage, not an assumed single chemical mechanism, dictated the sequence of the restoration work. Evaluating the extent of the chemical decay required meticulous evidence discipline. Engineers could not rely on visual surface inspections alone, because the most severe degradation occurred deep inside the overlapping metal seams. The team conducted a detailed structural survey to determine which sections could be retained and which required replacement. In several areas, corrosion had consumed enough material to eliminate useful load-bearing capacity. Defining the boundary between salvageable original metal and material that could no longer be trusted became a daily engineering judgment. The engineering team faced a strict procedural constraint. Restored structure could not be attached responsibly to metal whose condition had not been established. Reconstruction, therefore, proceeded only after affected areas were cleaned, inspected, and, where necessary, dismantled for closer examination. Corrosion was removed or treated, and any section that no longer met the project's structural requirements was replaced. This forensic cleaning and neutralization phase added a massive time penalty to the project timeline. It forced the volunteer team to disassemble sections of the remaining fuselage simply to arrest the ongoing degradation. The chemical legacy of the agricultural operations fundamentally dictated the pace and physical limits of the initial hangar work. Once the internal environment was stabilized and active corrosion had been brought under control, the team faced the next mechanical hurdle. Could the compromised structure be repaired without losing the original Boeing geometry? The restoration of the internal systems required a qualified authenticity standard. At the Renton facility, more than 100 volunteers contributed across the life of the project. Many of them retired aerospace personnel familiar with Boeing drawings and manufacturing practice. The team sought to return the aircraft as closely as practical to its wartime B-17F configuration, favoring original equipment and period-correct details where available and accurately fabricated replacement components where surviving parts were unavailable or unusable. Authenticity was judged against Boeing drawings, wartime specifications, and the physical evidence remaining in the airframe. The objective was not merely to create a convincing public display, but to rebuild the aircraft with unusual engineering and historical fidelity. Because the civilian agricultural operators had systematically stripped the bomber of its military configuration, the volunteers needed to replace nearly every functional internal system. This inventory included heavy defensive turrets, internal armor plating, oxygen distribution lines, and complex analog computers. None of these assemblies had been manufactured in decades. The procurement process required searching global salvage yards, surplus military auctions, and forgotten industrial storage facilities. The volunteers transformed into investigative researchers, tracing obscure part registries and verifying component numbers against original Boeing technical orders. The search for a genuine Norden bomb site illustrates that forensic discipline. A friend of engineer Paul Nelson reportedly located an original unit in a warehouse at Iowa State University. Nelson bought it for $5, restored it, and donated it to the museum. The story showed that authentic equipment could still surface in unlikely places, even decades after production had ended. This forensic sourcing logic applied to every switch, bracket, and wiring harness brought into the Renton facility. Each sourced component entered a strict verification workflow before it was cleared for installation. Parts were individually inspected for hidden structural flaws, tested for material integrity, and cross-referenced against the official 1943 assembly drawings. If a salvaged part failed to meet the original operational specification, it was discarded and the logistical search resumed. The engineering team consistently refused to compromise the zero-hour standard to save time or accelerate the project schedule. This meticulous supply chain operation successfully gathered the necessary authentic raw materials to rebuild the military interior. The volunteers accumulated a massive inventory of original equipment, but this logistical success created an immediate physical problem. The aircraft fuselage still lacked the critical load-bearing architecture required to support these heavy military systems. Reinstalling hundreds of pounds of authentic equipment required exact original attachment points. With authentic components sourced, how could they be safely tied into a chemically weakened fuselage? Restoring the internal architecture of the aircraft was governed by a strict geometric limit. Before the volunteer engineering team at the Renton facility could reconstruct the missing primary load paths, they had to solve a fundamental handling problem. The physical requirement was to hold a 1943 fuselage in exact alignment while simultaneously cutting out and replacing compromised structural sections. The affected bulkheads were not merely partition walls. They maintained the circular cross-section of the fuselage and transferred aerodynamic flight loads across the outer aluminum skin. Altering them had severely degraded the structural integrity of the airframe. Reconnecting damaged or altered structure required exact sequence control. Removing support without adequate bracing could allow the thin outer skin to sag, twist, or lose local alignment, greatly complicating the rebuild. Temporary stabilization was therefore essential before invasive structural work began. Published accounts do not fully document the precise configuration of the temporary fixtures used. The restoration should therefore be described in general terms. The airframe was stabilized, Damaged structure was addressed section by section, and alignment was monitored throughout the work. Once the handling geometry was locked in place, the meticulous cutting plan commenced. The Renton volunteers removed the spliced and severed structural frames section by section. The physical labor of drilling out thousands of old rivets without enlarging the original holes required immense patience and technical skill. They operated under strict sequence control, never removing more structural material at one time than the temporary jigs could safely manage. When a compromised frame section was drilled out and extracted from the airframe, a fully authenticated replacement bulkhead segment was immediately aligned and riveted into the open gap. The installation of these replacement structures followed the project's broader authenticity standard. The engineers matched the replacement structure as closely as practical to Boeing drawings, using appropriate aluminum, rivet types, metal thicknesses, and period-correct assembly methods. This restored the intended configuration without claiming mechanically identical performance to a factory-new airframe. Driving new rivets into older aluminum required exact pressure control to avoid cracking the surviving original skin. Every replaced internal frame was tied into the surviving fuselage stringers with absolute precision. The team continuously checked the longitudinal alignment of the fuselage throughout the riveting process to ensure the temporary jigs were holding the correct shape without inducing localized stress points. This phased reconstruction method slowly rebuilt the internal skeleton of the aircraft from the inside out. As each consecutive bulkhead was tied back into the primary structural network, the fuselage regained the rigidity and alignment needed to resume its load-bearing function. The temporary external jigs were systematically lowered and removed only after the internal frames had taken over that role. The restored structure could now support the recovered military turrets and interior hardware. Would this strict structural discipline yield a fully operational system or merely a static shell? The success of the interior restoration was judged against a demanding but approximate benchmark. Standard museum practice can accept cosmetic facades, but the Renton team sought a far more complete reconstruction. Published accounts state that approximately 98% of the military equipment required for the restored B-17F configuration was installed. That figure refers to the type and completeness of equipment present in the finished aircraft, not to hardware proven original to this individual airframe. Reaching that level of completeness required careful installation and constant reference to Boeing drawings. Each sourced or accurately reproduced assembly had to be placed at the correct station and connected to the appropriate mounts. As the compartments filled, the airframe ceased to resemble a stripped agricultural tanker and again took on the integrated form of a wartime heavy bomber. Merely installing the equipment satisfied only the visual requirement. The team also worked to return as many systems as practical to functioning condition. Contemporary restoration accounts describe the result as approximately 95% operational, while the museum now summarizes the aircraft as functional apart from its demilitarized guns. The figure should therefore be treated as a reported benchmark rather than an exact audited percentage. Restoring that level of functionality required extensive electrical, mechanical, and systems work. Components were cleaned, repaired, rewired where necessary, lubricated, and connected so that many restored systems could be demonstrated under ground power. Published accounts do not substantiate every claimed arc of turret travel, every actuation sequence, or every internal connection described here. The defensible conclusion is that most systems were returned to working condition for controlled museum demonstration. This level of functional integration required rigorous ground testing and evidence discipline. Volunteers ran detailed continuity checks on thousands of feet of original specification electrical wire to ensure the 95% operational threshold was safely achieved without introducing a localized fire risk. Every moving mechanical linkage was verified against historical technical orders to guarantee proper mechanical clearances and travel limits. But did this interior reconstruction guarantee historical accuracy on the exterior? By 1998, the restoration had reached a major milestone, and the aircraft was flown from Renton to Boeing Field. Work, relocation, and preservation activity continued after that flight, so 1998 should not be treated as the absolute end of the project. During this final phase of the restoration, a significant trade-off edge emerged between the identity of the volunteer workforce and the strict historical baseline of the museum. During the project, the museum and restoration community adopted the name Boeing Bee, drawing on an earlier Boeing emblem and the aircraft's connection to the company and the volunteer effort. Commemorative nose art was created to honor that restoration history, rather than to imitate a combat identity. The curatorial question was how to distinguish the aircraft's documented wartime configuration from the restoration history created decades later. A factory-fresh B-17F would not have carried personalized combat nose art at delivery, and this aircraft has no confirmed combat identity to reproduce. The museum therefore treated Boeing Bee as modern commemorative artwork, not as evidence of wartime service, and retained the name and design as a tribute to the restoration, the Boeing connection, and the people who saved the airframe. With the physical configuration strictly locked, the museum faced a final operational decision regarding the long-term preservation of the airframe. Because the aircraft was proven to be highly functional, with the vast majority of its internal systems restored to working condition, it was mechanically capable of continued flight operations. However, routine flying introduces severe environmental and mechanical constraints that directly threaten forensic restorations. Flight operations expose aluminum airframes to cyclic structural fatigue, atmospheric moisture, and ultraviolet degradation. More critically, operating a vintage heavy bomber requires continuous inspection, approved maintenance, and replacement of any component that can no longer be shown to be airworthy. Federal regulations do not automatically require modern substitutes for every historic part, but continued flight can force difficult compromises between authenticity, traceability, serviceability, and safety. To reduce weather exposure and preserve the restored airframe, the museum placed it on static display beneath the roof of the aviation pavilion. The pavilion is open to the surrounding air rather than fully climate-controlled, but it provides substantially more protection from direct rain and sunlight than an outdoor ramp. Static display also eliminates the cyclic structural loads of continued flight. The aircraft is preserved not as an active air show performer, but as a carefully maintained museum artifact. The aircraft remains in this covered configuration today as one of the most complete and authentic surviving B-17F restorations, not an untouched factory original, but a carefully reconstructed historical aircraft.